Hello everyone, I'm Xinyang Zhang from Penn State University. I'm here happy to present our paper, Interpretable Deep Learning Under Fire, at USENIX Security Symposium 2020. This is joint work with Ningfei Wang, Shen, Shouling, Xiapu and Ting Wang. We present an attack against interpretable deep learning systems in this paper. Let's first talk about the deep neural network's interpretability. While DNNs achieve superhuman performance on visual recognition, language understanding, and game playing, they are often criticized as black boxes. It is hard for humans to understand how a deep neural network arrives at a particular decision. This opacity may limit the application of DNNs in safety-critical domains due to their unpredictability. Therefore, intensive research efforts have been spent to develop techniques to explain DNN's behavior. In our paper, we consider 4 families of interpreters for the image classification task. All these algorithms generate an attribute map to highlight significant regions in the input image that contributes to the classifier's prediction. They are backpropagation guided, representation guided, perturbation guided, and model-based interpreters. Here we have an example. On the left side, we have an image classified as a flute with high confidence. On the right side, we have the attribute map shows where the darker region contributes to the model's prediction. An interpretable deep learning system consists of a deep neural network, the classifier, and an interpreter. Such design involves humans in the decision-making process. For instance, the explanation of a specific decision could help analysts debug their deep learning models. On the attacker side, it requires the adversary to fool both the classifier and the interpreter to break down the entire interpretable deep learning system. In this paper, we take a step towards understanding the security vulnerabilities of interpretable deep learning systems. Our approach is to develop attacks that simultaneously fool the classifier and the interpreter. The diagram here shows the workflow of our attack. Given a benign input of a fish, the adversary adds a penny perturbation to get an adversarial input. Then, this input will cause the classifier to misclassify it as a cat. And the input also misleads the interpreter to generate a target attribute map. Here we present the overall formulation of our ADV2 attack. The attacker crafts an adversarial input that triggers the target prediction CT and the target interpretation MT. We formulate the attack as a constraint optimization problem. We want to find an X that minimizes the magnitude of perturbation delta, such that Fx is CT and Gxf is MT. It is hard to solve this problem directly, because it involves nonlinear deep neural networks and complicated interpretation algorithms. We cast it as a regularized optimization problem as below. Here, L prediction is the targeted PGD loss, and L interpretation is the squared L2 distance between the generated map and the target map. Can directly apply the formulation in the previous slides to representation-guided and model-based interpreters. We propose 2 techniques for backpropagation-based interpretation. The gradient silencing interpreter outputs the absolute value of gradient of prediction confidence of class C for the input. Attacking gradient silencing involves second-order terms of the neural network, while for the ReLU function, the value is 0. Hence, we propose a gradient enhancement for ReLU during the backward stage. Besides, to avoid an empty attribute map due to the graded saturation, we apply the label smoothing to the classifier's target. Perturbation-guided interpretation. We take mask as the target interpreter. Mask uses optimization to find a small region, which greatly reduces the classification confidence of the target class when the region is removed. In this setting, we are faced with a bilevel optimization problem. We use an approximation approach that we alternatively update an estimation of optimal attribute map M star and input X. We also utilize an imbalanced update and periodical reset to stabilize our attack. We evaluate our ADV2 attack on the ImageNet dataset. Our target classifiers are ResNet 50 and DenseNet 169. We compare the ADV2 attack to the PGD attack. We set the target attribute map to the benign attribute map. The top table shows the attack success rate in terms of misclassification and prediction confidence. It shows our attack is as effective as the plain PGD attack. The two charts below measure the similarity between generated maps and target attribute maps. The left chart shows the L1 distance, and the right chart shows intersection over union. We could observe that our ADV2 attack could mislead interpreters to the target map, while the PGD attack fails to do it. We show sample inputs, prediction, and interpretations here. The first row are benign inputs. The second row are attribute maps for the benign inputs. The third and the last row show the attribute maps generated by PGD and our ADV2 attack. As we can see, we visually validate that ADV2 attack is better at fooling the interpreters. Discuss why our ADV2 attack is possible. We hypothesize that there is a gap between the classifier's prediction and the interpreter's interpretation. We conduct a random class interpretation experiment to validate it. We show the experiment in the bottom figure. In the first row, we first select target images from random classes. Then, in the second row, we get the maps of those target images. For the third row, we perform ADV2 attacks against benign inputs with another set of random classes, and set target attribute maps from the second row. The last row shows the interpretations of ADV2 adversarial examples. Note that the target and ADV2 inputs are fairly distinct, but with highly similar interpretations. The chart on the right side also indicates this. As we can see, our attack is possible even there are no dependencies in the target class and the target attribute map. Move one more step, and we hypothesize that limitations of existing interpretation models cause the prediction-interpretation gap. Different interpreters might focus on distinct aspects of DNN behavior. For example, gradient and intermediate representations. We perform an attack transferability test here. In each row, we have an adversarial input generated by ADV2 attack for one specific interpreter. Then, we inspect the attribute map of this input on the other three interpreters in each column. Ideally, for a fixed input, the model should have a fixed behavior to predict it. However, we observe that different interpreters focus on different regions here. For the last, we discuss potential of our ADV2 attack. Due to the low transferabilities of the attacks shown in the last slide, we could use an exampled interpreter. In this way, multiple complementary interpreters could fully cover DNN's behavior. We also propose an adversarial training approach for a model-based interpreter. We want to minimize the prediction-interpretation gap using adversarial examples. We feed a pair of benign input and ADV2 input to the interpreter and train the interpreter to generate distinct attribute maps for the two inputs. As we can observe from the third and the fifth columns of the figure here, the adversarially trained interpreters are more sensitive to the adversarial perturbations. The table on the right side also indicates this. In this paper, we propose the ADV2 attack against interpretable deep learning systems. We conclude our key findings here. First, the interpretabilities of existing interpretable deep learning systems merely provides limited security assurance. Second, the prediction-interpretation gap is one possible cause for the adversary to exploit both the classifier and the interpreter simultaneously. Third, adversarial training aiming to minimize the prediction-interpretation gap potentially improves the robustness of interpreters. I would like to thank you to my audience and my co-authors here. For any further questions about our paper, you can just send an email to me via the following email address. Any questions from the audience?